Welcome. In this video, we cover all the big ideas of section 7.3, isomorphism and planarity. We'll talk about isomorphism, planar graphs, and Euler's formula. Isomorphism, number one. One of these things is not like the others. So two of these graphs are very similar in some way, and a third one is fundamentally different. Which is the different graph? Take a second, see if you can identify it and why it's different, and then start the video again to check your work. Alright, so hopefully you identified B as the one that's different. And why is it different? Well, for me, one of the things I see in it is that it has two vertices of degree 3, and that's not different from the others. The others also have two vertices of degree 3. But what's different about this guy in the middle is that those vertices of degree 3 are not connected, whereas in the other two, those vertices of degree 3 are connected. And so if I imagine moving these around, I can take this first graph and I can move it around to make the third, but I'll never be able to move edges and stuff around in order to make the second. And this is the big idea behind isomorphic graphs. Notice the words. Iso means same, and morphic means shape. Graphs G and H are isomorphic if one can be moved around to look like the other. And so these two graphs here are isomorphic. If I take this top one and maybe I rotate it 90 degrees counterclockwise, I'll get a picture like this. And then maybe I'll take the two legs and I'll spread them out, and we get something like that. And then it looks like the picture down on the bottom. If G and H are isomorphic, then they have so many characteristics in common. They have the same number of nodes, the same number of edges, the same degree sequence, the same number of cycles, the same number of cycles of any particular size, etc., etc. Because moving graphs around, I'm not really changing any of these things. I'm not changing the number of nodes when I move something around, and I'm not changing how vertices are connected to each other. So anything that is fundamentally a characteristic of one graph is not going to change when it gets moved around. Example. Explain why the two graphs below are not isomorphic. You might want to pause the video and see if you can identify the difference. What is it that prevents one of them from being turned into the other? Alright, let me talk about some of the things that I observe. Well, first of all, they both have the same number of vertices. It looks like they each have 8 vertices. And on the left, it looks like I see some triangles. I see some cycles of length 3. There are 3 of those. On the right, I see some cycles of length 3, but I'm not sure that I see 3 of them, so that could be a difference. Also, on the left, I see 2 vertices of degree 4, but on the right, I don't think there are any vertices of degree 4. So definitely, I can't move one picture around to create the other. Take a look at this, and actually pause the video and give this a try. Find all isomorphic pairs among the graphs below, and then start up again to check your work. Give it a try. Alright, let's reveal the answer. It turns out that A and D are isomorphic, and B and E are isomorphic. Now, some people have a little difficulty seeing this. Let me show a demonstration of why these are the correct pairs. Okay, here we go. So I've made copies of A and D, and in this program, in GeoGebra, I can move them around. So let's see here. Maybe I'll take the A and change it into D. If I move that edge up, and I'll start moving this edge down. And look at that. I've turned A into D. And how about B and E? So what can I do to change B into E? Well, it turns out actually if I just switch the top 2 vertices. There we go. I've changed B into E. Explain why the following graphs are not isomorphic. Alright, take some time, give this a try. Alright, so they have the same number of vertices and the same cycles, I think cycles of length 3, but one thing that's different is that this guy has degree 5, and I don't think anything else on the right has degree 5. Alright, try this one. Why are they not isomorphic? All right, and let's see. Well, they actually have a lot that's the same. They have 6 vertices. They both have the same degree sequence. Every vertex has degree 3. So I think it boils down to the cycles in this one. On the right, I can see a cycle of length 3. But on the left, it turns out that all my cycles have even length, and you can confirm that. Or at least, certainly, there's no cycle of length 3. Planar graphs, the next big idea. The utilities problem. Can 3 utilities, water, gas, electric, be connected to 3 houses without any lines crossing? And this is a graph theory problem. The 3 utilities, I imagine those are the 3 points on the bottom, and somehow I need to connect them to the 3 vertices up on top. And I need to do it without any lines crossing. So how about the middle one? I can go there, there, and then, let's see, maybe I'll go around on the right this time to connect. Uh-oh, and now it looks like I'm stuck. For my third vertex on the bottom right, well, I can connect to one there, and I can even sneak it around and connect it to the left on top. But it looks like I have to cross at this point, at least as I've drawn it. So maybe I made a mistake. Maybe I need to go back to the beginning and try drawing it again, and then I can draw it. So this is a good puzzle to actually play around with for a little while for yourself. See if you can connect the 3 vertices on the bottom to the 3 vertices on top without any lines crossing. Definition: a graph is planar if it can be drawn on a plane surface without its edges crossing. For example, each of the graphs below is planar. So it doesn't really look like they're planar, right? Because we definitely see some edges crossing. But the key idea is that if it can be drawn without the edges crossing, then we call the graph planar. Here I have a little demonstration to show how these 2 graphs can be drawn without edges crossing. Alright, so here we are again in this program where I can move edges. And how about this one on the left? How do I draw it without edges crossing? Let me take this vertex on the top right, and I'll just drag it right in there. And now, no edges cross. For the graph on the right, it doesn't look quite as easy how to do it, but in fact, if I just grab one of these vertices on the right, start moving it to the left, eventually we see, look at that, all the crossings have been undone. So both of these are planar graphs. Now, here are 2 graphs that are definitely not planar. This one on the left is called a K5, and the one on the right is K33. The one on the left is called a complete graph on 5 vertices. I put 5 points down, 5 vertices, and then I connect all possible edges. The one on the right is called a complete bipartite graph, and I have 3 vertices on the left that are not connected at all, 3 vertices on the right that are not connected at all, but all possible connections are made left and right between the 2 sets of 3. It's sort of funny, but these 2 graphs form kind of the fundamentally smallest graphs that you can find that are not planar. I'll explain that more in a second. More generally, I can make a graph called a K sub n. This is the complete graph on n vertices. It has an edge between every pair of vertices. K sub nm denotes the complete bipartite graph with the vertices a1 through an, so maybe you consider that a set a1 through an, and b1 through bm, like the set of vertices on the right, and it has an edge between each ai and each bj and no other edges. These graphs are also not planar. Kuratowski's theorem says that a graph is planar if and only if it contains no copies of K5 or K33. Here's an example. One of these graphs is planar and one is non-planar. Which is which? So it looks maybe a little obvious, right? The one on the right has more edges. It's probably harder to untangle. So yes, in fact, the one on the right is the one that is non-planar, but why not? Can you see it actually has a copy of the K33 inside of it? Here we go. So I've outlined in red the K33 that lives in there. Oh, and incidentally, sometimes the K33 is called the utilities graph because it's the graph that you get in the utilities problem. Euler's formula for planar graphs. Once a planar graph is drawn in the plane without edge crossings, we can define the faces of the graph to be the regions of the plane created by the drawings. So which regions are created? Let's see, I can count them. 1, 2, 3, 4, and 5. Because the exterior outside of the graph, that's another region that has been defined relative to the graph. And so I'm going to say that this graph has 5 faces. Here's a good question. Is the number of faces invariant? So I drew this graph one particular way, but you know I can move vertices around. I could draw this graph another way and really get something that looks very different. Will it still have 5 faces? Maybe I can draw this graph in a different way that creates a different number of faces. Let's take a look at this. It turns out that there is an interesting relationship between the number of vertices, faces, and edges. Let me do the first couple graphs, then I'll ask you to do C, D, and E. So in graph A, and we are allowed to have graphs with multiple edges or loops, but we just want the graph to be connected. The number of vertices is 2. The number of faces is 3. Don't forget, you always have to count the big outside face. And the number of edges is 3. In the graph for B, the number of vertices, 5. Number of faces, 2. Number of edges, 5. So there's some kind of pattern between the number of vertices, faces, and edges. Go ahead, take some time, finish up the chart for the other 3 graphs, and see if you can figure out the formula that relates V, F, and E. All right, give it a try. Okay, welcome back. It turns out that the remaining numbers look like that, so hopefully you got those. And have you figured out the formula that relates V, F, and E? Here it is. This is Euler's theorem, well, one of Euler's theorems. If a planar graph has V vertices, E edges, and F faces, then V plus F equals E plus 2. So check that formula against all those numbers you saw on the previous slide. V plus F equals E plus 2. And in fact, this tells us something interesting that I asked earlier. Is the number of faces invariant? And it is, because as I move a graph around, the number of vertices certainly doesn't change, and the number of edges certainly doesn't change. And so, consequently, the number of faces doesn't change either. All right, so we've covered a lot in this lesson, but I've also raised a few big questions. Next lesson, we're going to prove Euler's formula using induction, and we're going to prove that K33 is not planar, and we will also see that K5 is not planar. So I will stop here, but we definitely have some interesting things to look forward to in the next lesson.